In this video, I discuss change of order in double integration. I explain it through an illustration. I will be evaluating this particular integral where r is as in the figure. The equation of this line is x plus y equal to 1. And there is another line which passes through these 2 points, 0 comma minus half and 1 comma 0. The equation of this line is y minus 0 upon x minus 1 equal to half. So the equation of this line is y equal to half of x minus 1, and the equation of this line is x plus y equal to 1. The region R is the collection of all these points. I will first carry out integration with respect to y. In doing so, x will be treated as a constant. X will be kept fixed. So let me fix x. Let's say here at this particular point. So x is going to be constant along this line. Okay? This is going to help me decide the lower limit and the upper limit of y. So once x is fixed, what is changing is y. So along this line, y is changing, and it changes for y corresponding to this particular point up to the y corresponding to this particular point. Now what is the value of y for fixed x for this particular point? This particular point is on this line, and therefore you can get the value of y from this equation. Y is equal to half of x minus 1. Up to, what is the value of y at this particular point? That you can get from this equation. Y is 1 minus x. So if you consider what is here, dx is a small thickness of the strip. It is actually so thin that x is hardly changing. Integration over R means carrying out integration over all such strips over this region R. The leftmost position of the strip will decide the lower limit for x, and the rightmost position will decide the upper limit for x. Therefore, the leftmost position is when this strip coincides with the y-axis, and therefore x will be 0 there, and the rightmost position of such a strip coincides with this particular point for which x is equal to 1. This is equal to integral x equal to 0 to 1. Okay, so I integrate with respect to y, treating x constant. So what I have is x y square upon 2, and the limits will be y equal to x minus 1 by 2 up to y equal to 1 minus x dx. This is half of, I pull this 2 out, integral 0 to 1, upper limit, replace y by 1 minus x, okay, the 2 is already out, minus x times x minus 1 by 2 square dx. Okay. So when you calculate this, the value turns out to be 1 upon 32. You can check this. I hope this is clear. Now let me show you how to work out the same integral with the reversed order. First integration with respect to y and then with respect to x. And after that we will see the advantages and disadvantages. So let me clear off the calculation. Okay, so I wish to carry out integration first with respect to what was done earlier. I had carried out integration first with respect to y. Now I am going to integrate first with respect to x. In doing so, for this part of the calculation, y will be fixed. Let me come back to this diagram. The region R is the collection of all these points. So if I fix my y here, y is constant along this line. If I fix my y somewhere here, y is constant along this line. Now there's a difference in these two lines. If you look at this particular line, it starts on the y-axis, but it ends on this line, x plus y equal to 1. Whereas if you look at this particular line, it starts on the y-axis, but it ends on this line, whose equation is y equal to half of x minus 1. So I cannot set the limits for both the strips in one go. So what I do is the following. This is equal to integral over R1 xy dx dy plus integration over R2 xy dx dy, and I call them as I1 plus I2. The first one is I1 and the second one is I2. Let's find the values. But then this calculation was done in the previous video. Assuming that you have already seen it, I will write down the value. This value had turned out to be 1 over 24. So I have just reduced my task to that of calculating I2. Let me do that. Integrating with respect to x, so y is fixed. Okay, so I fix y. So this is my region R1, this is the region R2. In R2, y has been fixed. Let us say it has been fixed here. So one is integrating over a thin strip which starts on the y-axis and ends on this particular line. That will decide the lower and upper limit for y. Y equal to 0 to y equal to. So what do I get for y from this equation? So y is equal to half of x minus 1. Alright, so the integration has been carried out over this strip, but then I have to do it over all of R2. So I need to fill R2 with all strips of this kind. The lowest position of this strip will correspond to this particular point, which will give me x is changing, so the value of x at the leftmost point is x equal to 0, and at the rightmost point the value of x is 2y plus 1. Please note the correction. Okay, so once I have carried out integration over this strip, and since I need to carry out the integration over all of R2, I fill R2 with strips of this kind, and the lowest position of such a strip would correspond to y equal to minus 1 by 2, and the topmost will correspond to y equal to 0. This is equal to integral I integrate with respect to x, so what I get is x square by 2, y as it is, y is a constant. Alright, put the limits as x equal to 0 to x equal to 2y plus 1 and then with dy. This is equal to integration from minus 1 by 2 to 0. I can pull this half out, and what I have now is y times 2y plus 1 squared minus 0 squared. This is what I get. You can proceed ahead and calculate this value. Now this is something which we are very comfortable with. This value turns out to be minus 1 over 96. Please check it. So I, which was I1 plus I2, is 1 over 24 plus minus 1 over 96, which is 1 over 32. All right. So we get the same value. So when you compare the two calculations, the first part of the calculation was when we had integrated first with respect to y and then with respect to x. We did not have to break the region into two parts. Whereas if you first integrate with respect to x and then with respect to y, you have to split the region into two parts. And I think the reason is clear to you now. So since we have to split the region into two parts, it brings in some tediousness in the calculation. So before you decide the order of integration, you would like to keep this in mind. So choosing the order of integration little intelligently can reduce the tediousness of the calculation. That is the point which I wanted to make. Thank you for listening.